Good morning, ladies and gentlemen. My name is Cees Glas. This is the pronunciation in Dutch, but very difficult for you, I think. I'm working at the University of Twente in the Netherlands. It's over there. And I've been working there since 1995. And before that, I've worked for about 12 years in CITO, which is the National Institution of Educational Measurement in the Netherlands. And the coming 2 days, I will present you some ideas about educational measurement and psychometric theory, some practicals, and some discussions about the things that we do in our research, and that might also be of use to you. I'll start this presentation first by framing a little bit the surrounding of our research. So the setting. The setting, and that is very important to know, is about high-stakes testing and big surveys. So the things that I will present to you apply if you have a lot of data. So if you do research and you have 20 students in a classroom, this does not apply. This is about high stakes. It's about big samples, about lots of students. So my work is started in the Netherlands at the CITO, Educational Measurement, where we do the centralized examinations in the primary and secondary education. Then we have several other projects and connections. The first one is, for instance, with the Law School Admission Council and the Graduate Record Examination in the United States. They also do a lot of things like test equating and high-stakes testing. These projects mainly focus around entrance examinations to universities. In the Netherlands, we don't have that. There are no entrance examinations to universities because everything is taken care of in centralized examinations in secondary education. Then we do a lot of research for testing on demand, item banking systems, and computerized adaptive testing. The way that is, for instance, used in the Netherlands in the Open University. So there you have a situation where you have test hubs all around the country, and students buy courses, they do a course, and then they go into a test hub to select a test, which is then delivered to them by computer. Comparable systems are, for instance, the TOEFL, Testing English as a Foreign Language, which is a test by ETS. And also ACT, American College Testing in the United States, does do a lot of things like that. Licensing in the United States, that takes place a lot. For instance, nurses have to obtain licenses to be able or to be allowed to perform certain tasks. That also goes with testing on demand systems. And then a lot of our research focuses around large-scale educational surveys. And these can be national or international. For instance, in the Netherlands, we have PPON, which is a kind of survey that monitors all over the years the level of education in the Netherlands. Comparable surveys are also done in America, like NAEP. And then we have the big international surveys, which probably are well known to you, like TIMSS and PISA. We were involved in the last cycle of PISA in 2009, where we did analyze all the background questionnaires. We developed the background questionnaires, we analyzed them, and we contributed to the final reports, and also written a couple of thematic reports. So that's where you have to place this kind of research. I will talk about educational measurement, and I will frame it in this presentation this morning in a very specific situation, and that specific situation is test equating. So I will use test equating as a kind of vehicle to introduce you to the ideas around modern testing theory and modern psychometric theory. And I will end this presentation with a real example, because we actually do this in the Netherlands. We do test equating and maintaining standards of examinations in secondary education, and I will tell you a little bit about the practical consequences and the difficulties that we run into. So imagine that we have a data matrix, and this is an examination. It's a very small data matrix. There are 3 students and there are 3 items. Of course, in reality, in the Netherlands, there are, for some examinations, 100,000 students, and usually there are something like 40 items. But this is only for didactical purposes, so I only have 3 students and 3 items. And in this data matrix here, I have the responses of the 3 students to the 3 items. So the items are the columns, the rows are the students, and this is year 1. Then 1 year later, we have 3 new students and a new examination, 3 new items. And of course, the important point is that there is no overlap in students between the years, and there is no overlap in items over the years. So this design, it's called this data collection design, is not linked. Students obtain total scores. So the total scores in this case are very simple. They are just the summations over their item scores, and we see that the first 3 students score 6, 12, and 9, and in a year later they score 12, 9, and 6. And the question that we want to answer is whether a score 12 by student 2 in year 1 is the same score as the score 12 of student 4 in year 2. So the question is, does that score represent the same level of proficiency? Okay. Now there are 2 things that we need to do. There are 2 steps that we have to take. First of all, in order to compare these 2 scores, we have to collect some additional data. And these additional data are collected to link the design, to somehow create some kind of link between the 2 data sets. And in this case, I've chosen to sample 2 students and give them a couple of items from the old examination in year 1 and a couple of items from the new examination year 2. This is just one way of linking it. There are many more, but I've chosen to use a linking group of students. And I collect their responses, and their responses are the 2 bottom rows of that table. That is step 1. Then the second thing I have to do is use a model. And in the end, we will use quite complicated models, item response theory models, and so they are statistical models, stochastic models. But here, for didactical purposes, in order to explain the essence of the method, I created a very simple model, which is a deterministic model, just to show you what the idea behind it is. So this is made up, it's not real, okay? And what I made up here is a model where I can represent my data as a sum of a student effect and an item effect. So if I look at row 1, student 1, you see that the summation in my model always starts with a 0. The 0 is the row effect, it's the effect of student 1. And so it goes on. The second student has a effect of 2, so there's always a 2 in the second row, and there's always a 1 in the third row, and so it goes on. Then secondly, the second part of my summation, so the second term, is a item effect, an item easiness in this case, and you see that that effect is constant within rows, sorry, in columns. So for item 1, for instance, you see that there is always a 2. Can I move around, or is this wrong? There's always a 2. So that's the effect of item 2. Then in the second column, there's always a 3. In the third column, there's always a 1, and so it goes on. then it turns out that this very simple model can represent my data, because if I go one step back, yeah, then you will see that the data, these are my responses, are perfectly represented by this stochastic model. So if you do the additions, you get the data. So this model perfectly recreates my data. And as I told you, it's made up. This is artificial. Okay? But from it, we see the principle of modern item response theory. Because what have we done? We have responses, let's call them x sub ni. N is an index for a person, I is an index for an item. These are the responses. And they are a simple addition of a person effect, a theta sub n, which is the proficiency level of a student. Why is that? Because if theta goes up, the score goes up. And an item easiness, beta sub I, because it's easiness, because if beta goes up, also the response goes up. Okay, so it's easiness. And it gives the essential feature of item response theory, and that feature is parameter separation. So you have responses, you have your data, and essentially what item response theory does do is distinguish between the level of the students and the difficulty of the items. It tries to take these two effects apart. And therefore we talk about person parameters, so these are proficiencies, and item parameters. These can be easiness or difficulty, but we'll see in a moment that there are also other possibilities for item parameters. So, the last column over there gives the thetas, and we were interested in the question whether student 2 had the same proficiency level as student 4. And now we see that student 4 is a little bit more proficient than student 2, because that student had a higher theta. So obviously that they obtained the same observed score, so obviously student 4 was presented with a more difficult examination because he has a higher proficiency level, or she has a high, I don't know what the gender is of that student, but I made that student up, so I could also give him a gender, or her a gender, but anyway, they have the same observed score, but the proficiency level of the student is higher to get that score. So the other examination, the first examination is easier, the second examination is more difficult. Problem of course is that I've made it up. It fits perfectly, it's a deterministic model, and in practice it does not fit. I mean, if I only have one or two observations that are not according to my model, then already I have to reject that model, because that model does not allow for any fluctuations. So what do we need? We need a model with parameter separation, but it has to be a stochastic model. It has to allow for fluctuations in the data. It doesn't have to fit perfectly. Then there were models thought up for that property, the property of parameter separations. And the easiest model and the simplest model that you can imagine is the Rush model. It's a very famous model invented by a Danish statistician, Georg Rush, about 1960. And it is for dichotomously scored items. So in principle, you can make it more complicated, but we'll take a look at dichotomously scored items. So it's good or wrong, right or wrong. Okay. Don't look too long at the formula, although it's a famous formula, but that's not essential now. What is essential is above in the nominator, we have again a linear combination of a theta, a person parameter, and a beta. And now, in this case, the beta is subtracted from theta. So the theta is the proficiency level, and the beta is the item difficulty. So the difficulty subtracts from the proficiency. And in that model, then you get the probability of a correct response, so the probability that the outcome variable x of a person n on item I is 1, that the person makes it correct, and it depends on ability or proficiency, you could call it, and item difficulty. Properties, theta is now unidimensional. Why? That's a question. Why should theta be unidimensional? When I say unidimensional, I say that all the children are ordered along one line. Okay, it's a unidimensional proficiency. Does it need to be that way? We don't know. And another thing is that the total score, the number correct score, is a sufficient statistic for proficiency. That means that if I know somebody's total score, I can estimate that person's theta. This is what the model essentially means. So this is what the formula means. On the x-axis, I have theta. So this is an ability scale, and it goes from -infinity to +infinity. So it goes all the way down there. And the y-axis is the probability of a correct response. And what the model actually says is very simple, because here's the probability of a correct response. And the model says that it goes up if you become more proficient. So it's monotone increasing in proficiency. Then it says that if you have a very low proficiency, the probability that you make it correct goes to 0. And if you have a very high proficiency level, the probability that you do it correct goes to 1. So that is not sensational. I mean, that's what you want to, that's what you expect. Still, the model, because it's a very simple model, does impose restrictions on the data. And one of the restrictions is the following. Here I have a curve for the probability of a correct response on one item. And above it I have the curve for another item. So these are two items. And one of the things that the model says is for every proficiency level, the order of these probabilities is the same. So everywhere you look on the ability scale, this is the difficult item and this is the easy item. This one always has a lower probability of a correct response than the other item. That is what the model says. A model is only a model if it can be rejected. So if you can get data that show you that the model is wrong, because otherwise it's not a model. It's just a data description. And the data can tell you that things go wrong in various ways. First of all, the response curves, the probabilities of correct responses might cross. It might be that for students of a very low proficiency level, the order of difficulty is different than for students of a very high proficiency level. Okay, so then the model is violated. Then the Rush model does not hold and you cannot use it. This is an even more realistic violation. It might be that you have multiple choice items, okay? And in multiple choice items, no matter how low your proficiency level, you always have the guessing probability of a correct response, because you can always guess the correct response. So what you see here is that this lower asymptote here does not go to 0. It is always above 0.20. So probably this was a multiple choice item with 5 response categories, and you can always pick 1 out of 5 no matter how stupid you are. I should not say stupid because that's not politically correct. No matter how low your proficiency level, you always have the guessing probability, so the model is violated. Yeah, it's not the Rush model anymore. To model all these things, we might make the model a little bit more complicated by adding parameters. Because we started out with a model where we only had for an item a difficulty parameter beta. Now we add 2 parameters. One is a discrimination parameter, alpha, and the second one is a guessing parameter, which leads to a formula which looks a little bit like the Rush model, but it has a number of elements added to it. And I won't go deep into the formula itself, but more into what it means and what the parameters mean. So again, we have here a dimension which is the ability dimension or proficiency dimension. I use these words interchangeably, okay? In education, it's usually more usual to talk about proficiency. So here I again have the probability of a correct response. Here I have my latent scale. The difficulty is the location of the inflection point of that curve, which represents the probability of a correct response. So that's the difficulty parameter. It can move, then if it goes in that direction, the item becomes more difficult. Then we have the discrimination parameter, which models the steepness of that curve. So it can be more or less steep. And finally, the guessing parameter models this lower asymptote. It gives you the probability of a correct response if you are very low in proficiency and start guessing. That is what the parameters mean. I'll take a look at the model in a different way now. Because I say it's a stochastic model, it's a chance model, okay? And to give you a little bit of a feeling what that means, here I have presented to you 9 items of a questionnaire that we often use of 30 items. And that questionnaire is constructed to measure somebody's length, okay? So usually you do that with a ruler, but why should it be a ruler? A questionnaire might be just as good. So I have here a number of questions which are all related to your length. For instance, the first one, I bump my head quite often. Okay? So if you are very long, the probability that you bump your head goes up. Okay? For school pictures, I was always asked to stand in the first row. Okay? So if you're very small, you must always stand in the first row. But it's a probability in the sense that, suppose that you are, usually you are asked to stand in the first row, but it might be that you are a very ugly child, okay, and that they place you in the back, that they can't see you. So it's a probability that you are asked to stand in the first row. Question 1 and 2 are ordered in a different direction. So if you say yes to question 1, you are high, you have a large length. Question 2, if you say yes, then you're short. So if you want to analyze this data, you have to recode the data so that they all point in the same direction. And so it goes on. In bed, I often suffer from cold feet. Okay, that is if you are long. But it's a probability again. It also depends on your wife, whether she is inclined to take the blankets or not. When walking down the stairs, I often take 2 steps at a time, and so it goes on. As a police officer, I wouldn't make much of an impression. And so we have a questionnaire of 30 items, which we actually deliver. Not only at our university, but also in several other universities in the Netherlands. That questionnaire is administered to students for didactical purposes. And then we analyze it with the Rush model. What comes out of it is a latent scale again. So the persons are located on the latent scale. This is their theta, so this is Jim and Joe, these are all people. Also, the items are located on that latent scale. And the latent scale means that Jim has a high probability of saying yes to items 3, 7, 5, 9, etc. But he's too short to say yes to the other items in probability. And so it goes on. Joe is very long. Joe dominates all these items, says yes to them, but these are too far out. Okay, that's the whole idea. And then finally, that's one of I think, the nice things about this story. If you correlate the outcome, the thetas of that test with the actual length of students, the correlation is extremely high. Yeah, that correlation can be very high, 0.80 or something like that. Okay? So that's another way of looking at stochastic models and the kind of models that we are working with. I started out now, so I'll now take a look at more complicated models. I started out with dichotomous responses, so it can be right or wrong. Then people sometimes think, well, does item response theory only apply to multiple choice questionnaires or something like that? That is not true. In principle, that the idea of parameter separation can be applied to any measurement, only you need more complicated models to model the outcome. And for instance, this one here is a model for polynomous responses. I have 5 response categories, which I code 0, there's a 0 there, 1, 2, 3, 4. It doesn't have to be that way, but in data sets where we analyze item response theory, we always start with 0. Okay, so in this case, we code them 0, 1, 2, 3, 4. And the model, again, is not very sensational as a model, because it says the following. Here we have a latent ability scale, and we have probabilities of observing a certain response, and this curve here is for a response 0. And the model says that if you have a very low proficiency level, then the probability that you respond in correct category 0 goes to 1, becomes 1. Okay? And then if you become more proficient, it goes down, and then here it goes to 0 again. If I take a look at the highest response category, if you have a very low proficiency level, it goes to 0, and then if it goes up, your proficiency level goes up, then also the probability that you score in the highest category goes up also. And then finally, the in-between scores. Well, if you, for instance, look at the score 1, if you have a very low proficiency level, it goes to 0. Why? Because you probably score in 0, okay, and not in 1. And then it goes up, it has a peak, it's monotone increasing and it's single peaked, and then at a certain point it goes down again. Why is that? Because then your proficiency level is so high that you probably score in a higher response category. Okay, so also in that sense, that model is not very sophisticated, but it is quite useful for proficiency measurement. This is about what you would like to see. This is the formula that goes with that model, and the important thing here, so it gives the probability that a person N scores in an item, on an item I, in a category J. J is 0, 1, 2, 3, 4. And there's a formula, but the important thing is that again you have a unidimensional theta, or you still have a unidimensional theta, so the students are still ordered along a unidimensional scale. And you have item parameters, but now many more, not just the difficulty level, but for every response category you have in principle a item parameter. Something like that. Then let's take it a bit further, but in order not to complicate life too much, we go back to dichotomous items. So right or wrong. And here we drop the assumption that it is a unidimensional scale. Okay? In principle, in practice, we then talk of multidimensionality, but it comes in 2 flavors. It can be within items multidimensionality. That means that if you respond to an item, then more proficiencies are at work within the same item. So you might have a mathematics item, but it might be framed in a certain situation so that you both need math ability and language ability to solve the item. Okay, so that is within items multidimensionality. The second flavor, the second kind, is between items multidimensionality, and that means you have a set of items which measure one trait, and you have a different set of items measuring a second trait. These traits are usually highly correlated. Think of something like maybe IQ and mathematics. It's highly correlated, but they are considered as two constructs, two things. And the items relate to either one of the constructs or the other construct. Okay? That is between items multidimensionality. Mathematically speaking, they are the same model. And before I present you the formula, I'll give you a little picture of what the models mean. So, instead of one unidimensional theta scale, we now have a two-dimensional space here. So these are two dimensions. Theta 1 might be, let's say, math ability, and theta 2 might be language ability. So every student is located here somewhere in that space and has a certain amount of math ability and a certain amount of language ability. And then here, this layer is the probability of a correct response. And that layer says the following: if your math ability goes up, the probability of a correct response goes up. If your language ability goes up, then also the probability of a correct response goes up. And if you are very high in both math ability and language ability, the probability of a correct response goes to 1. Okay? This is an example of a unidimensional model, and it's also a model because it articulates something about how you think that the response comes about. Because it says that the model is compensatory in the sense that you can compensate a low level on one ability with a higher level on another ability. So, for instance, if you would take a look at students with a probability of a half of answering the item correct, then they could be located on a line of proficiency in this space. So they could have a high math ability and a low language ability, or a high language ability and a low math ability. You can compensate things, okay? And whether that's realistic or not remains to be seen. I mean, you can have theoretical grounds whether you expect that or not. Then you have to go to other models, like conjunctive models or disjunctive models. I won't consider them here because they are quite complicated. But also the data, of course, can tell you, does this model fit the data or does it not fit the data? This is, again, the formula for that. And the important thing here is, again, we look at the denominator over here, and we say theta 1, theta n sub 1, theta sub n1 is the ability of a person on the first dimension. A theta sub n2 is the proficiency level of a person on the second dimension. And again, here you have these alphas, these discrimination parameters, and they tell you how important the two dimensions are for giving the response. So if the alpha is high, that dimension is important. And if the alpha, in principle, the alpha can be 0, then the dimension is not important at all. Okay? And this also gives the connection between within items multidimensionality and between items multidimensionality. If you have between items multidimensionality, only one dimension is important. Okay? Because an item then only relates to one dimension, IQ, and another item might relate to another dimension, mathematics. Okay? these models can be written up in various ways. And one of the important things to remember is that this multidimensional IRT model, if you write it up in a certain way, it is completely equivalent with what is called or known as, and probably known to you, as a factor analysis model. So a factor analysis model or an item response theory model, they're all versions of the same big family of latent variable models. So in that sense, statistics has many connections. Okay, so some of you might be familiar with factor analysis, and it's really very close. And the big differences only are related to the way that you estimate things. Okay. Then, this was a short overview of item response theory modeling. And now let's take a look at what happens if you apply this in real life. And this is a story about a real research project that has been going on for a very long time. I was involved as a psychometrician in that research project from 1985 or something up, and it has to do with equating the cutoff scores in the examinations in secondary education in the Netherlands. So in the Netherlands you have centralized examinations, so every year in secondary education the students participate in certain topics like Dutch language, English language, mathematics, stuff like that. So these are very large sample sizes. There is very much effort made in making the examinations comparable over the years. So the people writing these examinations, developing these examinations, really do their best to come up with something which is comparable over the years. So they do all their effort. However, the inspectorate started an investigation in trends about 1985, and then they found out that no matter how much effort you spend, there is still fluctuation and difficulty over the years. And since in examinations the data set is in principle not linked, if you would do nothing about it, the system would change without you noticing it. It could be that there is a downward trend in the level of the students and the level examinations, and together they go down, okay, and you wouldn't notice. So that's where the project started. So the problem, the level of the students and the difficulty of examinations fluctuate over the years. The objective is to determine a cutoff score, passing or failing, on the examinations in the same way, in some way that it reflects the same amount of proficiency level. So the proficiency level at the cutoff score over the years must always be the same. We have to take into account then the difficulty level and the fact that students change over the years, that there are trends. By the way, the fact that there are trends was noticed by these educational surveys, these national surveys, where we found that something was going on, but it didn't reflect in the examinations. Okay. We started the project by trying out several designs. And the first design that we tried out was the anchor item design. So what we have here is a representation of a data matrix, the same one as I started out with. So rows are students and the columns are the items. We have a reference examination, so there's a set of items which is, say, year 0, and we have a new examination, say this is year 2, and the data from these two blocks, from these two examinations, are in principle not linked. Okay. So we have to create a link, that's step 1, and we try that by using an anchor examination or an anchor test. And an anchor test was a test that was given to the students 2 weeks prior to the actual examination, but it remained the same over the years. Okay, so we did that for 2 years, 3 years, and we kept that anchor constant. That was the idea, and this was the kind of data matrix that we got from that. That design did not work for several reasons, and let's sum them up. First of all, it was always given the anchor test prior to the examinations. However, students study very hard the last 2 weeks, and they change their proficiency level. In principle, that's not so bad if all the students have the same gain. Yeah, because we want to model this with an IRT model, and there has to be a theta that represents their level, and if all the students would improve on their proficiency with the same amount, that would be not a problem, okay? But the problem is that they are different. Some gain a lot, and some hardly gain anything. And of course, Then there's a second problem, and that is the motivation of the students, because these anchor tests are not given in examination conditions. An examination condition is a high-stakes test, and they do their utmost, while the anchor test might be given in very different situations. And the quality of your data is then determined by the extent to which you can present it as a high-stakes test. So to give you an example of a very a low-stakes test, for instance, it might be so low stakes that students just guess the responses because they are not motivated at all. They just guess. And that might be that the probability of a correct response would be 0.50 or something, or that if it's multiple choice, even lower. Okay? So you have guessing responses, and you want to use that as an anchor for an IRT model where the probability of a response is given by an item parameter. And you cannot put that together in one model. That does not work. So these responses on the anchor test tell you nothing about their proficiency level. They are not very good predictors. You could also say that the item ordering in the anchor test and in the examinations is different. Well, what does that mean? If you have an examination situation, you really have item ordering, and you have ordering of ability along this scale. But if everybody is guessing, everybody has the same proficiency level, and all the items are the same also. So you don't gain any useful information. Then there's a practical problem, and in education measurement you also have to deal with practical problems. In high-stakes tests, if you use an anchor test over the years, it becomes known. And that is because teachers are humans also, and also because teachers are in a very high-stakes situation, because the examination does not only evaluate the student's proficiency level, but also it evaluates the level of teachers. And in the Netherlands, that works in a very strange way. As such, the teachers are not evaluated because they have very different populations of students. But within a school, it's different because you have a language group, you have a mathematics group, you have a science group, and they all, if you have students of low proficiency level, because you have students from low socioeconomic background or something like that, okay, your results should be low. However, if one of the teams is different, so everybody is at a certain level, but the language group is way down, okay, then you have a problem, because on the same population relative to your colleagues, you do bad. And in the Netherlands, that leads to scrutiny of the inspectorate and what is happening, what's going on. So also for the teachers, it's a high-stakes situation. So the bottom line is to keep an anchor test secret is maybe an illusion. So, and all these effects together, they violate the statistical model, because the statistical model says you have an ability, it's theta, and you can model the responses of the students using that model, and it does not work. In the Netherlands at this moment, we have two designs. One of them, which I will present to you, and this is for the modern languages, English, French, etc. And it works like this. You have examination in year 1 and the examination in year 2. The moment that the second examination is given, we have available linking groups in a different stream of education, and they all get a small part of an old examination and a small part of a new examination in this way. Okay? And that creates the link. Why does that work? It works because I did not tell you about things like random sampling and stuff like that. Why is that? Because in principle, in the model, every student brings with him or her their own theta. Okay? So the proficiency level is explicitly modeled, and at this point, I have not made any assumptions about distributions and sampling and stuff like that, although that has to be in order, but it's not in the model. So it means that the level of the thetas of the students in a linking group need not be exactly the same as the theta levels in the examination situation. Okay? So they can be a little bit better or a little bit worse. And that in the Netherlands creates the possibility of sampling in another stream of education. The way that we do it, I won't go into detail because it's quite complicated, but you could imagine that at the end of secondary education, if you have the mathematics examination, you could go to students at the university in year 1 at mathematics, something like that, okay? Because the proficiency is still the same. Their level is maybe a bit higher, but their proficiency is the same. That's an advantage of IRT, but you cannot take that to extremes, of course. So if you have at the end an end term of mathematics in secondary education, you cannot go to primary education to find your linking groups, because there the proficiency is not available. Okay? So there is a certain freedom to choose your respondents, but you must be sure that the same construct, that the same ability construct applies. And then secondly, something practical, how do we do that? Well, first of all, because that's always the problem of secrecy, first of all, these linking groups are sampled with groups of teachers who actually make the examination. They are scattered all around the country, because in the Netherlands the examinations are made by teachers who get 1 or 2 days a week off to go to CITO and are taught to write items. Okay? And the second thing is that the old examination does not really exist. It's a kind of mixture of many old examinations with calibrated items, items where we know the item parameters, and we relate to that kind of anchor, that kind of old examination. But in principle, nobody knows what it is. Okay? Because it doesn't exist, because it's made up of 10 other examinations. So that's how it works in practice. This is in the Netherlands, and finally, last example is in a project where we have made some collaborations in Sweden. It's the Swedish Scholastic Aptitude test. It's a kind of entrance examination to the university. In Swedish it's called the Högskoleprovet. And there we have a design like this. Simplified a little bit, but it works like this. An examination there consists of, say, 40 items. As an example, say it has 40 items in blocks of 10. Then in that examination is put an extra block of 10 items that do not count for the final mark. Okay, so it's a kind of pre-testing. So there are 4 blocks of items which give you your final mark, but hidden in there are items in the 5th block which do not count. Okay, the students do the examination. They do not know which items are the pre-test items. Then if they come out, they no longer have the items, but they do get a total score. They know that there are 40 items which are relevant and your score is 25 correct or something like that. They know that there were items hidden in that which do not count. And in that way, you get responses which are really high stakes. Because students do not know, they're doing an examination, but they do their best on every item. Okay? So in that way, small blocks of items are pre-tested in a real examination situation. This is a little bit simplified because here I create from these pre-tested items a new examination in the next year. So then you have a linked design. In principle, the design is much more complicated because they kind of pre-test for 5 years in a row in a very complicated design all over the country. But this, of course, is really a great design because there you get, first of all, you solve the problem of secrecy. And secondly, you get responses in a high-stakes situation, and these are really very good data. So that ends, I'm nice on time, that ends this presentation. My conclusion is this was a kind of introduction to IRT. We'll talk more about that in the coming days. It was around test equating, but there are many more applications of item response theory which are very important in educational measurement. First of all, we'll talk a little bit about computerized adaptive testing and optimal test construction. So IRT can help you to construct a test. An important issue is test fairness and differential item functioning. It has to do with the question whether certain groups are not disadvantaged by certain items or certain tests. The application of item response theory in big educational surveys like PISA, but also national surveys. So that was the introduction to IRT. Thank you very much.